Good afternoon, ma'am. Sir, good afternoon, sir. Once again,
Good afternoon.
uh, welcome you, sir. And now it's over to you, sir. You can start.
Thank you. Good afternoon, everyone.
I'll allow them, sir, to talk.
Yeah.
Yes,
Just
sir.
tell them that whenever somebody is speaking, at least at max one should speak, and when the question answer is over, they should mute yourself.
Sure, sir.
Yeah. So this is basically the just Google this IBM Quantum Experience. You will have this link, and just tap on that link. So it will ask you for login information. So I have provided my this Gmail for logging in. So if you have some other like Facebook or some ID, then you can using those. You can log in. Just a second. You will have once you open this quantum computing IBM, you will get this kind of interface where you are provided option to sign in. So there are numerous options like LinkedIn, Twitter, Gmail. So I am logging using my Gmail account.
So I need to create the account
No need to create, just you need to sign up.
through any Gmail ID. Is that so?
Yeah.
Okay.
So once you have once you log into the website, this kind of interface you will find there. So basically, this is the platform over cloud, which is provided by IBM, where lots of IBM provided their quantum computers for experimentation, free of cost, and also a quantum simulator to test your jobs there.
Okay.
So you see here, these are the devices available. That is IBM Q San Diego, that is IBM Q Athens. So these devices are named after the city they are deployed. So like this computer is deployed in Santiago and it is available online and it consists of 5 qubits. So
Is it safe to log in through Gmail?
yeah, safe only. But the thing is that whatever you do on this IBM quantum computer, those are basically stored on their server. So if you are not doing anything secret, then no problem. So username password is safe. Don't worry about that.
Okay.
So see here, these are the systems available. That is Valencia, that is Vigo. So but it's basically these are available devices. And how many jobs are running on those devices? 56 jobs are currently being run. So basically these are actual quantum computer, physical quantum computer are deployed in those cities by IBM. And through cloud, we are able to run our job on those devices. So before running this thing, we should have what are the things available here and how we can use them. So these are the devices available. And if you see here, one of this IBM Q16 Melbourne. So these are available devices. And there is last one option is that is IBM QSM simulator, 32 qubits. So what this simulator does is, this is not an actual quantum computer, but it can simulate quantum computer. So where 32 qubits are available, so you can create a circuit consist of maximum 32 qubits on this simulator and can test. And there are options. So you can test here. So basically, most of the time, what we do is we just first test our jobs on this quantum simulator available there with 32 qubits. And once we are sure that our algorithm or our circuit is good, then we will run on actual devices. Because actual devices, there is some waiting time. queue is there. So once the queue is over, then your job is run, and it is automatic system. So once you submit your job, if physical device is currently available, or then it will result will reflect back in a second. But if there is some waiting queue, then it will take some time. So if time is more, then it will email to you once your job is done. So results are mailed to you after the successful completion of the job. So the idea is that there are various physical devices and a quantum simulator available here. We can use all of them. So if you go to this home, this is the thing. Yeah. Here we are seeing these systems. What are the systems available? They are online. And there's this device, if you see, it is under maintenance. So it is not available. So whatever device is currently running, those will be available here. And you can also view the retired system. So those systems are not being used nowadays, but they were earlier online available. So this is the thing. In the jobs column, whatever jobs you have there with, so see here, 2 days ago, I created a job with this ID and I ran into a quantum simulator, and run mode was fair share. Basically, everybody is given equal importance to run their circuit. So in the job history, you will have all the jobs which you have run, and job ID is there. Okay. So you can also like check what was there that job. You can see the results also, circuit also. So next come to the important part of this, that is circuit composer. So this is the option here, circuit composer. So what does this provide us? This circuit composer, as the name suggests, we can compose a circuit here. Here, if you see, so there are 4 qubits, qubit 0, 1, 2, 3. We can add qubits also. So let's suppose we are having this 5 qubits. Okay. So this line is showing the qubits. So we have selected 5 qubits for us for our circuit, and these are the gates available. Seeing the gates, this row is having the gates. Everybody is able to listen me and follow me?
Yes, sir.
Yes, sir.
Okay. So these are the gate. And this H denotes the Hadamard gate. This plus denotes the NOT gate. And that is control NOT, C NOT. And that is Toffoli, basically control NOT. And that is swap gate. So it is like using the basic gates they have made available directly here. Otherwise, if it is not there, then we can derive the gates. Some of the basic gates and some of the derived gates are available for ready to use. Others gates, if we require, then we can design according to our problem. So this is basically swap gate. This is identity gate. What does it do? If we apply this identity gate on a qubit,
same as the input.
Yeah, qubit will be remain same in same state. And as I explained this Z gate, what does the Z gate does? It changes the phase of one state. It converts state 1 to -1.
Plus to
0 remains
minus.
same. 0 remains same. 1 changes to -1. What is this S and T gates? Specific phase gate value pi by 4 and pi by 8. Here it was pi. This S and T are having phases pi by 2 and pi by 4. Okay. So those are called S and T gates. Basically, they are phase gate only. Phase gate value here pi in case of Z. Here pi by 4 and pi by 2. What is this T dagger? T dagger is nothing. If we have a T gate,
Transpose.
Transpose conjugate. If there are some this imaginary value, then conjugate is there. So basically, transpose conjugate of this gate is T dagger. Similarly for S. So if you know this, remember the matrix of this S gate. Then what was that? Just a second.
5.
So we will go through those slides so that we can connect.
I'm not able to log in. I don't know why.
You can okay. Someone can help. What is the issue there in logging?
I could log in, sir.
So can you help the
I'm
other?
trying. I'm trying on MacBook now.
Okay, so it's not an issue. Uh, you can try with some other like LinkedIn or
Yes.
this. You can use that also if not able to using the Gmail. Otherwise, you can create your IBM ID also. So these were the phase gates we have studied. So basically, what does this phase gate does? It changes the phase by theta degree. Okay, of that one state. So if phase value is pi by 2, then it is called S gate, and this is pi by 4. So what will be transpose conjugate of this T gate? So rows will be converted into columns, and if some value a plus iota b is there, then it will be a minus iota b. So it will be 1 0 and 0 e to power minus I pi by 4. Are you getting me? So the basically T dagger will be here, sign will change. It will be e to power minus I pi by 4. So what is that basically doing? It is changing the phase
It
by
is wrong.
minus pi by 4. This T gate does the phase change by pi by 4 plus pi by 4, and T dagger is basically e to power minus I pi by 4. So basically it is changing the phase by minus pi by 4 radian. So here becomes, just let me share my screen. I think you are not able to see the slides which I was referring. Just a second. I think, are you able to see the slides also?
Yes, sir.
Yes, sir.
Earlier I was referring the slides, but I did not share. So what I was telling here is that this is the T gate. Are you able to see the T gate here?
Yes, sir.
Yes, sir.
Yes, sir.
So what I was telling that this T dagger is basically complex conjugate of this matrix. So complex conjugate of this matrix will be just this sign will change. This 1 0 will come here, then again G 0 or e to power minus I pi by 4. So just the phase value is negated in this T dagger case. Okay. And sometime, yeah. So what will be the okay, X gate? What will be the X dagger? X dagger will be that only the row will be converted into column. So it will remain same. So X is equal to X dagger. So in that case, if we apply 2 times this X gate, then it will be identity. Are you getting me? Okay, now let's come back to this slide. So these are the gates available here. So I told that what is this T dagger gate is basically complex conjugate of this T. So it was doing phase by pi by 4, then it is doing by minus pi by 4. And it is for solid dot is for control qubit. So if you want to make some qubit control, that will basically change the other one. It will not change itself, but it will change other qubit. And it is to reset the state to zero state. This Z is for, are you able to see the screen?
Sir.
Yes, sir.
Okay, if any, yeah. So this is the measurement gate. So finally, what we do is we do some, we initialize the qubits, we do some gates, and then we do some computation, and finally we measure. So after measuring, what happens? This information fall into some classical bits. So that is done by this measurement. And if you want to some kind of if operation, then you can using this we can do. This is barrier.
Barrels.
Barrier, what it does is it just stop the computation. Like if I put barrier here, then everybody will come to this point. Then only other gates will be applied after this barrier. So at this barrier, every gate will be executed first. If I put barrier somewhere, let's suppose if I put barrier here, then before it, all need to finish the computation and then only the gate will be executed.
So your voice is not clear. It's breaking.
and these qubits, we will construct our circuit. So what I told.
So you were not audible.
Yes, sir. When you were talking about the barrier, you were not audible.
Oh, sorry. So, okay. So let me repeat again. This barrier was just to stop the computation till that point. Let's suppose I put this barrier here. So then what will happen is that at this stage, all the computation before this left side will complete first. So if somebody has completed this computation earlier, then it has to wait here. Then only once all complete till this state, then only they will proceed to write of this. So barrier just delaying or stopping some computation, so that all can be in sync. So you can simply drag and drop the circuits here. I can cut here. So what is the thing? So by default, these qubits are initialized with zeros. Keeping this thing in mind that initially they are in state 0. Okay. So what I'm doing here is, let's suppose I am having only one qubit. Okay. So if I apply, it was earlier 0, and then I applied Hadamard over it, then what will happen? It will become 0 plus 1 by root 2. So 50% time it will be 0. So this is amplitude. So this state vector is showing the amplitude of that state. What is the amplitude of 0? That will be 1 by root 2. So what will be that amplitude? 1 by root 2, that is basically 0.707. For 0. For 1 also, amplitude will be 1 by root 2. Is it clear?
Yes, sir.
So let's suppose if I put this NOT gate here, then what will happen?
Just opposite.
So 0 will become 1 first.
1.
Here. Then on 1 we are applying Hadamard. So that will convert into 0 minus 1 by root 2. So minus 1 is basically, so one state will be having amplitude minus 1 by root 2. Okay. So sign is negative here. This red
So
color
it is going in opposite phase.
Yeah. So this red color is showing the opposite phase. This blue in one direction and red in other direction. Okay. And if you see the probability amplitudes, then what will be the probability amplitudes? Mod square of this amplitude. That is basically 1 by root 2. So it will be 1 by 2. See here. What I am saying is this is the amplitude and probability is basically mod square. So mod square it is 50%. And it is having amplitude negative minus 1 by root 2, but still mod square will be
positive.
That is 50%. Is it clear?
Yes, sir.
So let me add me one more qubit. Okay. And I'm remove this. So initially these two qubits are 0, 0, and we are applying two Hadamard gates. So what we are getting here is all the 4 state we are getting with same amplitude, that is 1 by 2, and probability 1 by 4. Is it clear?
Yes.
So let's suppose if we take one more qubit, then what will happen? So here what we are having, initially
1
we are
by
having
8.
Yeah.
1 by 8.
So probability is 1 by 8, that is basically 12.5. That is probability is 12.5% of each, and amplitude is like this. That is basically, I think, 1 by how much it? 1 by square root of 8.
Yes. Yes, sir.
So 1 by square root of 8, and this all states are there.
2 to the power 3 goes there.
So is it clear now? 1 by root 8 is this one.
Sir.
And
Yes,
the square is basically 12.5.
Yes, sir.
So what we are saying here is that initially you are having only 3 qubits which were in state 0, 0, 0. So only one state was there earlier. So let's see how this progresses. So there is an option called inspect. So if you use this inspect, so initially all will be 0, okay, and now once we apply Hadamard on first qubit, then what will happen? So this right side qubit is the
Same.
first. See here, earlier it was 000, only one state was there, this one was there. Now we apply first Hadamard. So what will happen? This first qubit will be 0 and 1 both. So it will become 000 and 001. Are you getting this thing?
Yes, sir.
Or the second this thing, yeah, qubit 1 and qubit 2 are fixed. So that those are basically 00, and this first qubit is in 0 and 1. So we get this kind of states. Now proceed with the second amplitude. Now what is happening? Earlier we are having this 2. So on this 2, what is happening here is that this 0 become 0 plus 1, and in this also this becomes 0 plus 1. So we are having 4 states. Okay. Now if we apply Hadamard on third qubit. So basically what is third qubit here? This one. This one is our third qubit. So if we calculate from right to left, this is first qubit. Keep this thing in mind. This is the first qubit, then second, and then third. So leftmost is the third qubit corresponding to this Q2. Okay. So what we are saying here is that we are applying Hadamard on third qubit. Let's suppose this is our third qubit. So if we apply Hadamard, so then this third Hadamard will work on all these states corresponding to this qubit, leftmost qubit. So this will goes to 0 plus 1, and this will goes to 0 plus 1. This will also goes to 0 plus 1, and this will also goes to 0 plus 1. So what will happen? See here. So this one state is splitting into 2. So totally we are having 3 2 to the power 3 states here. So I want to explain this thing that once we have initial state 000 and we apply Hadamards, 3 Hadamard in this fashion, then we are with this only these 3 qubits. We are having this all 8 amplitudes of 3 bits with us. And if we apply something on one of the qubits or 3 of this, then all of this 8 will modify. All of this 8 can be modified. Are you getting this thing? Quantum parallelism, I want to explain you.
Yes, sir.
So let's have a new circuit. So we need to close this. Yeah. So these are the amplitude and these are corresponding probabilities. So probability is clear to us. Just mod square. Na? So to close this inspector. So this inspector is for our visualization purpose only, so that we can see step by step effect of the gates on the qubits. Is it clear? On actual device, what will happen? You cannot see or look in between. If you look in between, then states will be destroyed. So quantum system is like you cannot probe in between. Whatever you supply this thing, and you will finally observe it. So what finally you will get? With this probability is 000, with this probability 001, those are the things which you will measure. If you look in between, then this entanglement or this superposition will be destroyed. So what we do is we create our circuit and we just finally observe this. But this inspector is kind of simulated kind of thing. So in simulation, we can do step by step progression of the circuit. We can see. So it's very useful. So now let's go to that. How did we created that entangled state or Bell state? First we apply Hadamard gate, then control not gate. This was the circuit. Are you able to recall?
Yes.
Just a second. This is the thing. So initially we initialize with 0 0, and then we apply header mark, then control node. So the same thing. Are you able to see the slides?
Yes, sir.
Yeah. So here we are doing. So by default, this Q0 and Q1 are initialized with 0 from the platform only. So we need to make them 0. Then we are applying header mark. Then we are doing C node. So we can also, like in the inspector, we can see what is happening here. So after this header mark, what will happen? Second qubit is 0. So this is our second qubit. It will always 0. Here 0, and here also 0. But the first qubit will go into 0 and 1. So first qubit here 0 and first qubit here 1. Initially it was 0 0 here before this header mark, and after this header mark implementation we will have this state. It is because that this first qubit can go into 0 and 1 both state, but second qubit will remain in 0 state. So here we see this is our left qubit is the second qubit. It is in 0 state, but first qubit is in 0 and 1, and the probability are 50% of getting 0 0 and 50% of getting 0 1. Now we move to the next step. C note we applied, and after application of C note we are getting this state. So as we have seen in during the circuit implementation, what we were doing is this first qubit is control qubit, this one. So in this case first qubit is 0, so nothing will happen on this 0 0. But in this scenario, this first qubit is 1, so it will change the second qubit to 1. So this 0 1 will become 1 1. So is it clear? After application of this C note, that state become 1 1. And if you see here, these are the amplitudes. That is basically 1 by root 2, 1 by root 2, and probability is 50%, 50%. So this is basically our Bell state, and we can have different Bell state by simply just, let's suppose if you put not here, then what we will get. So see here, so we told here that if input is 1 0, then we will get 0 0 minus 1 1 by root 2. So it is same as this one only, but the phase is changed for 1 1 state. So see here, it is 0 0 1 1 only, but phase is opposite. Okay, that is shown by this red color. It was in blue, so phase is pi here. Okay, so now comes to this half adder circuit. Can we draw the half adder circuit here? Somebody can tell me how to create the half adder circuit?
Toffoli gate for
So here we
carry.
have to
Any one of you, let me
first
guide.
we have to make XOR and then other for AND gate.
Okay, so for that, what are the gates
Toff-
required? Toffoli?
Yeah, one Toffoli gate.
One Toffoli. So this qubit 0 and 1 are control, and target is
Yes, sir.
Q2.
Yes,
And
sir.
then other C note gate.
C note, yeah.
Okay. So now this is the circuit, I think, and we were saying that at this second qubit, first qubit will remain same. Second qubit will give us sum, and third qubit will give us carry. Okay, but our input is here. Input is 0 0. Okay, so what should be the sum?
0.
Let me, yeah. So it will remain 0, and sum and carry both are 0. Okay. In case of input 0 0, so sum and carry both will be 0. So let's make this input as 1. So what I need to do is, if I apply not gate here, then this 0 will become 1. So what is happening here?
The answer should be 1, the output, and
yeah. So sum should be 1 and carry should be
1.
no
0.
Carry should be 0. So here this first will remain 1. So our answer is in second and third qubit. Okay. Our answer,
Yes, sir.
sum is in second qubit and carry is in third qubit. So there is no carry. So if you see here, third qubit, that is 0. So what is our answer? Basically 0, 1, 1. So if you see
0,
here,
1, 1.
so this one
Correct.
is the first qubit, that is the same, but the second qubit is showing our sum, that is 1. Here 1 plus 0 is basically our sum, that is 1, middle qubit.
So now NOT gate should be put on Q1. So Q0 will be 0 and Q1 will be 1, 0, 1.
Yes, correct. So let's do it. So here what we are doing is our input bits are 1 and 1. So our carry should be
okay.
1.
1 and sum should be 0.
0. And it is
So
1,
1, 0, 1.
1, 0, 1. Correct. And probability of getting it is also 1. Probability is 100% because we are running this thing on a simulator. Okay. So in simulator we are assuming there is no error. If we run this on an actual device, then there may be some error, and due to that we will get some errors. Some other state also we will find. Correct one is this one only, 101. Ideally we should get 101.
No, sir, I didn't understand why this probability is 100% over here.
Okay, so what I am saying is that on running this circuit, if you run this circuit, you will get 101 state as an output.
Okay.
So only this, if you measure this thing, just a second, let me do this thing for you. What we are doing is we are measuring this qubits in classical
results.
bits. Yeah.
Okay.
So what will happen is these 3 qubits will collapse into this classical 3 bits, 0, 1, 2. So in classical bits, what is the assignment we will get? We will get 101.
Okay.
If we run one time or several times, we will get 101. But just a second. Here we see this examples. So till now I am clear that this is the circuit and this is the measurement operators which we are applying. So we will be getting answer in this 3 classical bits. So here we are saying that classical bits will be 101, and using these classical bits we can see that our answer is basically sum is 0 and carry is 1. If is, let's suppose if we get 101 in our answer, then we know that the third qubit is having this left qubit is having our carry, middle qubit is our having our middle bit is having our result, and first one is the original bit. So how to run it on the simulator? So there are various options. So what we did is we created the circuit, okay, and there are this option shorts. So if we do it for one time, then one answer we will get. But it is better to run experiment several times. So generally we put it into 1024 time. Okay, there is option to run it up to 8192 times. So if we run this on simulator, click here. Sorts we have fixed. So our task is being run. Our job is sent here. See here, our job is completed. So clicking this job, we can see the answers that what we are getting here. So this kind of thing we will get. This is our job ID. So what we are getting at answer is 101. Okay.
Okay.
100% probability. It is because we are running it on a simulator. Let's rerun it on the actual device, because actual device is not perfect because of various things. Just a second. So I have deleted the result, but okay. So so let's come back to here and just let me redraw the circuit. So our circuit, just redrawing the purpose. So if you don't apply this measurement gate, then there will be some error that you have not measured the. So run setting, I am going, and instead of this, what we want to do is, so system what we want to use is, let's suppose this Valencia is having only 2 jobs. So we'll try to run on this device. Okay. Valencia we have selected, and we are going to run this on this device. So see the state here, our job is sent to this Valencia. Okay. And here it is written that our job is in queue, and in a minute we will be getting the answer. Okay. So it is completed. Okay. Everybody is with me? Now we are going to see the results. So basically what we have done is, we have run the circuit on an actual device. Okay. See here. Can anyone explain why this is happening? So we have run that experiment 1000 times. Okay. So out of those 1000 times, 67% time I am getting 101. But sometime I am getting these also, or other options also. So if we run this experiment one time, suppose, then we can get 101 also, 100 also. So what we do is, since it is probabilistic, this quantum computing itself is probabilistic. So what we do is, we run the experiment several times, so that we can get this kind of probability distribution. And seeing this distribution or histogram, we can decide that 67% time we are getting 101, then it means the other answers are due to error in quantum computer. What kind of error are possible there? There are gate errors, because the gates which we have applied. Okay, so why this is happening? Because of errors in quantum computer. It is because of gate error, read error, and initialization errors, and there are many. Qubit lifetime is also there, so qubit also distort sometime. So due to those imperfection, this kind of results we are getting. And this kind of devices are called noisy intermediate state quantum devices, NISQ devices. So what is that means is, basically they are having they are small devices with tens or hundreds qubits, and they are having errors. So but for our practical purpose we can use it, because if more than 50% we are getting something, then it is probably our answer. This thing is clear?
But sir, previous time it was giving the 100% answer.
Yeah, so that we run on quantum simulator, where we assume
Okay.
that this operation are perfect without any error. If
And
our
here,
actual quantum computer,
this
the physical device, actual device, quantum computer is not accurate.
Yeah.
Is it clear or not?
not
Okay.
means is a different basis you are using, or what? I don't understand.
No. Actually, whenever I am
What
applying
is this
this,
Valencia and what was that previous one, sir?
yeah, Valencia is a actual quantum computer, and this simulator is just a simulator, where we are assuming that there is no error in the gates. The gates are perfect, qubits are perfect, and whatever operation we are performing, it is performing according to our circuit. But
Okay.
in actual device, due to this various kinds of noises, errors occur in the quantum computation on physical devices. So it is like you can say that there are some error in the actual quantum computer because of this gate error, qubit errors, other errors, lots of errors are there. Due to that, we are getting this kind of answer. Simulator, we assume that gate is not having any error, qubit is perfect. So everything we are assuming perfect there. So if we assume perfect, then we will get perfect answer, 101.
Okay.
But practically, when we implement this quantum computers, there are these engineering challenges. Due to that, this kind of error occurs, and we get this wrong answer also with fewer probabilities.
So this Valencia is showing the physical, means the actual performance.
Yes, yes. Actually, we have run on a quantum computer, Valencia, named Valencia. Maybe it is situated in some city, Valencia. So we are actually done this computation.
Okay.
So you understand one thing, that there are the devices currently we have are not perfect. So remove this kind of error. There are error correction codes also available. But to implement those error correction, we need more qubits. But we are currently, due to engineering challenges, we are having devices with only few qubits. So to correct, to make a one qubit behave perfectly, we need hundreds of qubits. This is the challenge. To make one
Okay,
qubit.
sir, got it. Thank you.
Yeah. So
sir, the simulation we assume ideal conditions, no sir?
yes, yes, yes.
Practically, some problems will come.
Yes, yes. So practically this thing will happen, and this is the exactly thing happening. Okay, but still it is useful because we have run the experiment 1,000 times, and 1,000 times if you are getting this 101 with high probability, then it is our likely answer. So we can discard this thing. Okay, and we can assume that 101 is the answer.
Sir, if there is any chance of getting 50% percentages, suppose probabilities, in
Yes,
such
yes.
case, how can we proceed, sir?
We should increase the number of shots. Let's suppose we have done it for 1,000 times now. If it will do for 8,000 times.
Yes, sir.
Still if it is 50-50, then we should improve our algorithm, or maybe both the answer are correct.
Okay.
Maybe both the answer are correct, because let's suppose we are having this Bell state, okay,
Yes, sir.
and we run this on actual physical device.
Yeah.
Then what will happen? Around 50% we will get 0. Around 50% time we will get 1 1.
Yes.
So maybe 40% time I get 0 0, and 60% time I'm getting 1 1. So both are correct in that case. If maybe there will be two answers to one problem, those are also correct.
Okay.
If you are getting after various more number of shots also, you are getting the same two answers, then
And
maybe
the
both are
probability,
correct.
yeah.
Both are correct.
And it depends on the quantum computer which we have taken. Sir, suppose in this case you have taken this Valencia, right?
Yes.
Suppose if you take other type of other device, maybe
Yes.
other computer,
Okay.
does this result vary, sir?
Yeah, it depends on how many errors, how erroneous that device is. Let's
Yes, sir.
suppose that device is near to perfect, then our this probability will increase and other will decrease. And if the
Yeah,
device
that's
is perfect, then we will go to 100 or 99 something.
okay. Because
If
earlier you have shown many other quantum computers also,
yes, yes,
right,
yes.
in this side.
Yeah.
So
Yeah.
if I run in another device
So
by
maybe
taking other device, the result may vary.
yeah, very perfectly, very.
Yes. Okay.
So, but all the devices are having similar kind of error. So it's not like
But the
that.
result can be expected. The
Yes,
result
yes,
can be maybe this 101 probability will be more in all the cases.
yes, yes. And if it is not, then device is not correctly implemented.
Okay.
Is it clear?
Okay. Okay. Yes, sir.
So see here, what happens is that what are these timings here? First is created, you created it. Then what is happening is here is this transpiling. What is this transpiling? We are assuming that yeah, transpiling we should see if it is transpiled or not. See here, this was our original circuit. Is it? It was the circuit. Anyone?
Yes, sir.
This is
Yes, sir.
circuit we draw.
Yes,
But
sir.
computer run this circuit. Actual physical quantum computer implemented this circuit. Why? Because that device might not be having this control node gate. Okay.
Okay.
So what it will do is it will create using
The
elementary
same.
circuits, elementary gates within. Okay. So what it does is this is the circuit actually run on the physical device. This was our logical circuit, and it was converted into this physical circuit that was run on the device, because device is having only these kind of gates, and this control node is not available. See here, there is no control node. See here, So what it does is, I have shown in the presentation also. That if tuple is not available to you, then let's suppose tuple is not available to us and we want to use tuple. So we can construct tuple using those gates, T gate, S gate, and C node gate. So you got the idea?
Sir, I didn't attend your first lecture. Maybe this is from that first lecture.
Yeah. So what I was telling in that session is, if we don't have control node gate with us, then we can make them using basic gates available to us. Let's suppose we are given this T and S gate and C node gate, and there this T star and S star. So what we can do is, if we draw this circuit, then this circuit will implement this tuple gate. So the same thing is happening here. As this device, Valencia, is not having CC node operation, control node available with it. So it did implement using the basic gates here. So here we see, if you see, we are only having these 4 gates only, but here we are seeing numerous gates. So those were used to implement this tuple. Okay.
Yes, sir.
So maybe our circuit is small, but transparent will be larger, or sometimes smaller also, because this IBM also does the optimization. Let's suppose if we put some extra gates which are not having any effect, then it will compact also. Sometimes gate is not available, then it has to derive the gate using the existing gates, and sometimes some redundant computation is there, then it remove also. Let's suppose if you are having this plus 2 time, so not 2 time will have no effect, so it will simply remove this plus gate. Getting me?
Yes, I got it.
Okay, so this was the graphical interface on which we put these gates and we did this thing. There is also a language called quantum assembly language. Okay, so this is the circuit, and what is corresponding assembly code is there that we can see here. So this was our original circuit. So circuit was in the diagram form. If you can see, first is on qubit 0 we are applying NOT gate, and then we are applying NOT gate on the first qubit. So see here, these are some libraries include. So basically we are having 3 qubits in our circuit. So declared 3 qubits, and classical 3 bits are there. So first we apply NOT gate, denoted by this X on qubit 0. Then we did X on qubit 1. Then we apply CCX, basically control node, tuple. And where this Q0 and Q1 are the control bits, and Q2 is target bit. See here, this Q0 and Q1 are control bits, and Q2 is target bit. See here, and then we apply control node from 0 to 1. Okay, and then we apply this measure gate. So we measure on classical bit 0, and same 3 measurement. Okay, so this is corresponding to our this circuit. So you can switch in between, like if you are not good at programming, then you can just simply drag and drop these gates and create circuit. If you are good at programming and you want to not do this kind of thing many times, so simply write this kind of code, it will do. And what is this transpiled circuit? So it is equivalent to this. Here we see, this is the circuit, original circuit, and this is the transpiled circuit. So corresponding QSM code is here available. Okay, so see here, to implement those gates, control node gate, it does this many gates there. Okay, so but we need not to bother about this transpiled circuit. It is taken care by the IBM platform. You just need to draw your or code your program, and it will be compiled according to the hardware available. So let's suppose it is not Valencia, some other device is there which is having other topology, then it will be configured accordingly. Okay, so let's go back to the.
Sir, what about the performance, sir, in such case? Suppose if it is transpiling that circuit,
Yeah,
the performance remains same, sir, because
no,
the circuit,
it will
whatever we
degrade.
are giving.
It will
Yes,
degrade,
sir.
na?
Yes,
Here
sir.
we are
That's
using
what.
only 3 stages, no?
Yes, yes.
So what do we call it? Circuit depth is only 3.
3.
Here depth is increased drastically.
Yes.
So it will degrade.
So due to this may be the reason to get that probability less also, right?
Yes,
Earlier
because
what?
more number of gates, more error is there.
Yeah, error will be more, right?
Yes. Otherwise, it could be having around 90.
100%. Yeah.
No, not 100.
Uh-huh.
100 means you are assuming that these all gates are perfectly available.
That's what I'm saying, sir. Suppose if that Valencia is
Huh.
having the same original circuit, which is having the Topoli
No.
gate and C0 gate exactly like this one, we would have got more probability, right?
Yes, yes, correct.
Yeah.
But in that case also, if they are
Maybe
not
some error.
100% perfect, yeah, a
Oh.
small error will be there. Because these
Okay.
are not perfect even this NOT gate is not perfect.
Okay.
Even if you think of this thing that this is there, that if you initialize this qubit with 0, it is also not perfect.
Okay.
So sometimes in out of 100 or 1000, it is not, sometimes it is not 0.
Yeah.
So these kind of errors are there. Due to that, this happens, and for that, to overcome that, we have to run the circuit several times to get a probabilistic histogram, and we can decide the correct answer.
Okay.
Anyone have any doubt here? So these were the number of shots we did. So if we do for more, then slightly this probability will also increase. So we see here this 845 million second were done for transpiling. 1 second for validation. So validation, it's this actual device does in itself. 3 seconds it waited in the queue, and 5.7 seconds to run the device, to run the our circuit, transpiled circuit. The transpiled circuit took this much time. Okay. So I think this thing is clear to everyone that what are the features available and how to understand them. So let's suppose if we the same circuit. So this is the circuit for creating equal superposition of 0, 0 and 1, 1. Okay. So let's run it on that Valencia only, or maybe we can choose some other device also. Let's run it on Valencia only. So as these gates are available, Hadamard is also available natively, and C0 is also available natively. So job is in queue. So we will get better answer with less error. So ideally we should get 50-50% probability. So we will get similar answer there. Not like that one is with 20% and other is with 80%. Yes, our job is in queue. Let it complete. Okay, still it is transpiled. Okay, it is running. So it is converted into this one. What it is so Hadamard was not available natively. So what it does is it uses this RZ and square root X and RZ gate to create Hadamard. So like these gates are available with it. Using these gates, it constructed this Hadamard. So see here, for one gate, it is applying 3 gates. So the error is introduced by, let's suppose there was only 0.01% error in one gate. So that error is increased here. So let's answer, let the answer come. It's still running. So it is still running. We will see it later on. So let's suppose if you do one thing, suppose that we are having this control node gate we are having, but we don't have control Z. Suppose so we can like this. So what we are doing is we are telling that here that we are having this control not operation, but we do not have control Z. So if you want to do control Z, then just put header mod before this plus and after that. This will work as a before doing that, yeah. So that will work as a control Z gate. So what does the control Z does? Okay, let's before that I think we should have control gate only. Z gate only. So here what I want to show you is we are having this NOT gate, but we don't have Z gate, suppose. So by putting edge header mod gate before and after, it will behave like a Z gate. What does Z gate does? Anyone? Anyone? Z gate changes the phase of one state. So suppose here input is 0, so it will remain same. Okay. So let's run it on settings. We should change. Instead of Valencia, I am taking as a simulator only. Okay, so see here what is happening. So on measurement also we are getting 0 only. So we will get 0 only because initial input was 0. So ZGet does nothing on 0. But let's suppose, so basically what I want to show here is that using this plus, basically NOT get and H, we are deriving ZGet. Okay. So ZGet changes the phase of one state. So let's suppose I make it 1. Okay. So then what should be the answer? It should be -1. So this plus make it 1, and then we apply this Z gate. So these 3 gates are consist of Z. So if we apply it over 1, then it will change the phase. So if you see using this inspect, so initially after this plus what we are having? We are having only 1. So 0 become 1 here. Then we apply header mod. It will become 0 and 1. Okay. Then we apply NOT.
1 and 0.
Then we apply header mod. So it will become -1. So what I am telling here is using this kind of thing, we can do whatever gate is not available to us, we can derive them also. Okay. And if you run this kind of circuit on actual devices, there are still errors in this thing. Ideally, we should get -1 here, but if you run on actual device, there will be some error. So let's see the output of that earlier one, where we did this Bell state circuit run. So there we should get ideal answer should be 50-50%. See here. What should be our ideal answer? That should be 50-50% of 0, 0 and 1, 1. But what is happening here? 49% time we are getting 0, 0, but 41% time we are getting 1, 1. And sometimes we are getting this also. But we can see here that almost 49% and 41. These are the top two answers we are getting most of the time. So if we run it for more number of time, then almost 48% of kind of thing, or 46, we are getting these answer. So probably these two highest probability amplitude will be the correct answer, namely 0, 0 and 1, 1. Is it clear or not?
Clear, sir. Thank you.
And why we are getting these two states, 0, 1 and 1, 0?
Some gate error or something.
What are the errors, possible errors?
Gate error, sir.
Yes, gate errors. Qubit error also.
Qubit error also.
Qubit error, gate errors, readout errors. When we try to read on measurement, na, that time also error occurs.
Yes, sir.
So it is because of those. So I think we are done with that. So just a second. And if you want to do a control node operation, control Z. So simply what we can do is something happened. Let's close it. So okay. So I think I am successfully explained to you guys how to use this platform and what is happening because of errors or something, and how to use this platform. I think I should explain more thing about this platform so that you can try it your own later on, how to explore and how to use this platform available to you. So these I explained here. So, okay. So here, if you see these colors, na, in the state if color is blue, then phase is basically 0. And this as this phase changes to pi by 2 around, then it is pink color. If it is opposite phase pi, then it is in red color. So basically when we see states here, the color also denote the phase. So here this phase is 0, phase angle is 0. These are the probabilities, and there is inspect option which is very useful. So step by step you can see how circuit is moving. Okay, in the view also you can have this different kind of things, this graphical editor, state vector, measurement probability. So measurement probability, if you don't want to see, then you can just remove it. And then we have this Q sphere. Okay, so here we are showing for one shot execution. Okay, where is that? If you run it for 1000 shots, okay, it was the earlier one. So in simulator we get perfect answer. Okay, this sphere is not shown here. Let's remove this. So this is the Q sphere, and what we can see here is, as a vector we see it is different from the block sphere. First understand this thing, that block sphere was representing a single qubit as a vector, and using this theta and phi notion we were representing there. Here what we are showing is that this 101 state is, so here what we are showing is that state, vector, and their phase values and probability. As a sphere we are showing that 101 is having the highest amplitude and highest probability, and phase angle is 0, and phase angle will be denoted by these colors also. So here it is blue, so phase angle is 0. So just to show all the states using those vector lines, that what is their phase, what is their amplitude, a different representation is provided here. So mostly this state vector is the meaningful thing to look into, and also like here. So here this lots of documentation is available for this platform, so you can go through it also. So where if you see here, yeah. So one thing I did not explain till now is that this quantum circuit is there, and corresponding quantum assembly language code we have already seen, and corresponding to that also IBM provided this quantum lab feature. So what does this provide is, using this quantum lab platform, you can write the code in Python language here online, okay, and submit it. So it will convert into that quantum assembly and it will transpile and run on the devices. This quantum lab also using this you can install on your device also and can directly use from this device also from the this browser also. So you can install this kind of thing. Qiskit is the software. This Qiskit you can install on your PC and program there and can submit, or you can do the Qiskit and this thing on cloud only. So we will see how we can do it here. So you can just here only you can open some notebook and you can write the code in Python here and convert them into quantum assembly and run there. So as this Python is user friendly and so for a small circuit you can just drag and drop and can do the things, but for bigger algorithms you need some kind of programming language, high level language, that is Python here. So using that you can also program. In the user accounts information, like so as I already explained, this simulator is available there and there are other backend configuration. So these backends are basically physical devices which we have seen, and fair sharing model is used to assign the execution time for circuits to all the user. And composer we have already done this. These gates are there, qubits we can take, state vectors, probabilities, and q sphere we can see. So in this editor also we have seen that we can create the circuit, save them in different formats, and can also share with others. We have also seen this run the circuits and view the results also, how to view the results and how to understand them. And there are other things also, like basic concepts and these algorithms are also available here. So you can understand or you can go through them. So it's a very good platform available to the researcher, and so they can try their program here. So
Sir, can you show a simple teleportation example? Is it possible?
teleportation, one issue is there, a sender and receiver kind of thing we are not able to demonstrate here.
In the same
Those
thing, we are not able to open two screens and we cannot do it.
not open screen. It is like sender and receiver and that classical communication in between.
Oh, that's required.
So,
Okay.
so that is the issue there. So in
Okay,
that case, what we require is a hybrid kind of system we require. So in that hybrid kind, classical thing can be done on that classical computer kind of thing, and the other things can be on quantum computer.
Okay, sir.
So any other thing which you like to explain me or clear me, I will clear you.
Okay. Thank you,
Because
sir. It was
these
excellent
things-
session.
But because this thing you need to explore yourself. If some issues come, then my mail ID is available. You can ask me also, and I will reply you.
Okay. Thank you, sir.
Yeah.
Sir, what are the possible applications that we can do with quantum?
Yes.
Yeah.
What
As we will-
applications are?
Yeah. So as in the yesterday lecture, you might have heard that if some physical phenomena you want to simulate on a classical computer, then it is very difficult. Why? Because the exponential space it will take.
Yes.
Like two particle if we combine, then space will grow exponentially. N particle it will be of size of 2 to the power n states. So if we do this thing exponential kind of thing on classical computer, then they will have limitation. After certain steps, they will not be able to perform that thing. But in quantum computer, we can easily see that the exponential space is provided by qubits in superposition, and we can operate on them. So basically, simulation kind of thing, physical phenomena or other things where simulation is required, those can be efficiently performed on a quantum computer due to this superposition and quantum parallelism phenomena. So like some uh, drug research also require this kind of simulation. So those can be done. And other applications we will discuss tomorrow when we will cover these shores and grovers. So those are able to do something which classical computers, even supercomputer, cannot perform in thousands of years, but a quantum computer with some qubits or 100 or 1000 qubits can do the thing in some time. But the same thing cannot be done on a classical computer or even a supercomputer in hundreds or thousands of years. So we will see those two application of this Dover search and source algorithm. We will understand them in detail also and have demonstration of the algorithms and what are their application, what are the threat by those algorithm to our crypto, that we will discuss tomorrow. So I think that there's those we should keep for tomorrow. And so if you understand that quantum parallelism phenomena, then you understand. So if we tomorrow we will discuss quantum algorithms. In that, this superposition, this quantum parallelism phenomena are widely used, and there is two other phenomena which is also used: entanglement and this constructive and destructive interferences. Have you heard this term yesterday?
Yes, sir.
So these kind of interference phenomena, entanglement, all of these things together are useful to design an efficient quantum algorithm, which will outperform the classical ones. But there are only a few quantum algorithms available to us, which are exponentially faster than the classical versions.
Sir, as we heard the news from Stanford University, some professors, they had research in
Yes.
electric vehicles. It was based on quantum computing. So, do you have any idea what topology they were using?
Currently, I don't have any idea. But the problem is that the processing
Their
quantum
purpose was means they were increasing the speed of the battery charging capacity was increasing over
yes.
there, and the
So-
size was small. Actually, I'm from electrical
Yeah, so-
branch, and
Yeah.
my topic is also means I'm searching
Yeah.
mainly based on the electric vehicles. But still, I'm not doing any PhD, but I'm thinking to do that, and that's why I'm searching a topic. So
Yeah.
here, that is the reason I came here for the quantum computing. So
Yeah, good if we were able to motivate you to pursue research in this field. So
thank you so much, sir.
try to enroll as soon as possible. Don't wait for this thing, that you should enroll for somewhere so that you will be in momentum.
Okay, sir.
So there are various IITs and other institutes are doing research in this quantum field also. So you can
Yes, sir.
see Google, or tomorrow I will also tell where are the
Okay.
research and opportunities available. So your question was that how they might be using this quantum computing in research of batteries. So basically, in batteries life, there are various parameters. Okay, maybe some
Yes, sir.
10 or hundreds of parameters will be there. So simultaneously, if you want to see all the effect of all these parameters on battery life, so basically
Yes,
simulation kind of thing only they will be doing, that if these are the parameters and how this one parameter change affect the others, or how the collective effect of those parameter can be used to optimize the battery's performance. So basically this kind of simulation study they might be using it.
so they were using the machine learning over there.
Yeah. So you understand this thing. This quantum computer provides us this quantum parallelism, and it is inherently suitable for simulation of physical systems where different variables are there, and those variables increase the state space exponentially. Exponentially means if you add one more parameter, then the state space will double.
Okay.
The quantum computer is suitable to handle those kind of situations.
Okay, sir.
Yeah. Any others?
Very good afternoon, sir.
Yeah.
Yes, sir. My name is Pratik Shankar.
Yeah, Pratik.
Yes, sir. Could you recommend any book for to study quantum theories?
Yes. One of the very good book is there. That is Nelson and Chong. Uh,
Okay.
just a second. I will show you the on the. You are saying you are able to see my screen?
Yes, sir. It's visible. Okay.
This one is the best book to start with.
Okay, sir.
Are you able to see it?
Yes, sir. It's visible.
Yeah. So a writer's name is Nelson and Chong,
Okay, sir.
and title is this: Quantum Computation and Quantum Information.
Quantum. I'm new to this field, sir.
Yeah, it's good
It
book.
was a very informative session, and I wanted. I am also looking to for PhD, sir, and
Okay.
I have given the entrance now.
Okay. Good. So
Uh,
the purpose of this FDP is that only that, and the nation we will be requiring researcher in this field of quantum computing and communication. So varied background researcher are required, like mathematics, quantum mechanics, computing, electronics, mechanical even also required. So if some of you pursue research in this field in future, then it is done. The purpose of this FDP is solved because today we are lacking expert in this field in our country.
yes, sir. Sir, and how would you? What is the? Is there any chances of combination of artificial intelligence and quantum computation, sir?
Yeah, there is. If you Google through this IBM website, then there they are saying that machine learning using quantum computing. So those kind of field I think will interest you. So the
Sir,
idea is
for
that,
some reason your voice is not audible, sir.
yeah, I think the network issue is here. Uh, is it audible now?
Yes, sir. It's audible.
Yeah. So I am repeating again. So if on IBM you will Google, then IBM has shown that using this machine learning, using quantum computing, they can have some quantum machine learning algorithms implemented. So I think those will interest you if you Google through. Then basically what they are doing is this: they are using some machine learning algorithm specifically suited for quantum computers and doing some faster pattern recognition or something. So you can Google that.
I am from electronics background, sir. I
Oh,
was looking for a combination of VLSI and artificial intelligence, sir.
so
But
if
I
you
found this very much interesting.
okay. So Pratik, for you that first session, na, how you can you propose some algorithm to reduce the number of gates or number of qubits or number of errors? So can somehow you can optimize those things. Like I require that error should be minimum. You take S number of qubits you require, but I require that error should be minimum. So can you kind of propose those kind of algorithms that reduces the error? Other parameters they can use to optimize this thing.
I'll try, sir.
Yeah,
Sir, one more query.
yeah,
Sir, you were talking about parameters. Will this
yes.
quantum computer work with parameter reduction or will it consider all the parameters?
No, it consider all the parameters. So
There is nothing, yeah.
currently the challenge is that we should have more number of qubits, because what is
No.
happening is that at that subatomic level, the to control all the qubits is the challenging thing. So each, like if you take the example of this superconducting qubits, what is happened there? There is some microwave pulses are thrown on a single qubit that can be an electron. So what we want to do is, let's suppose 1,000 electron is there, so 1,000 qubits are there. So using those microwave pulses, you want to precisely control each electron.
Okay,
So
sir.
those are in some very small area they are there, and to precisely control them is the challenge. So as of now, you will see that only 100 qubits quantum computers or less than 100 are available, and that too also with errors. So
Okay, sir.
to remove those errors, we can implement error correction codes, but but those for error correction also we require extra qubits. So the qubit scalability is the issue, and error is the inherent problem there,
Okay,
both in
sir.
the gates and qubits.
Thank you, sir.
Any other query? So you might be having my email ID, so you can write any query or suggestion or guidance if you require. Then you can write to me on my Gmail ID. That
Yes,
is
please, sir. Please share
Harish
your email ID.
harish.sahu, HARISH .SAHU @gmail.com.
Thank you, sir.
Could you repeat, sir? Harish dot
Sahu, SAHU
Hmm.
@gmail.
Okay, sir.
Yeah. Dr. Sunita, I am done.
Thank you, sir. It's really an honor to have you as a resource person.
Okay,
Because like in this area to say in depth and very nice presentation and all, really great, sir. Thank you, sir.
Thank you very much.
Thank you, sir.
Thank you
And
all of us for listening
Thank
to
you,
me
sir.
entire day.
Thanks for this wonderful presentation, and this is really amazing explanation. First time I really understood what is the quantum computing, and I'm feeling shame that I couldn't attend your first lecture. But
No problem. I
if
think it is available. It is available online or somewhere.
yeah, I will
Yes.
find it. Yes,
Yeah.
sir. I will find it. Thank you very much, sir. Thanks.
Okay.
sir, one request, it's better if you could share the PPTs to me so that I will share to the participants.
Yeah, that I will do.
Participants, it will be the great news is tomorrow also sir will be available with us, so you can hear from him. So it's the great news actually. Really, sir, because before starting also to say this name quantum computing, everyone is like, what is this quantum computing and all these things? But you started from the classical things and again slowly you come towards the quantum. It's really great, sir. Thank you, sir. Thank you very much.
Okay. Thank you.
Again,
Thank you,
we'll meet
everyone.
tomorrow, sir. Thank you, sir.
Okay.
Okay. Participants, kindly fill the attendance, and if any queries you have, you can ask me. Otherwise, tomorrow anyhow we will meet at 10 a.m. But all are requested kindly join in time. Thank you very much. Now I'm going to end the meeting.